Hi and welcome. Today we're going to show you how to use an oscilloscope to measure the voltage across a charging capacitor. This is a circuit you're going to be using. It comprises of a resistor in series with a capacitor. We're going to connect this circuit up to a power supply, a DC power supply here. Now a power supply has a current dial and a voltage dial. We make sure that the current dial is fully clockwise, and for this circuit I'm going to use 5 volts DC, so I just need to tune that a little clockwise to get that at about 5 volts. So there we are, that's at 5 volts, and then we switch it off. The next stage is to connect our circuit up. We have the power supply. The positive of the power supply is going to connect to our resistor like this. Sometimes you might just want to give it a quick wrap around the crocodile clip just to get a good connection, and the negative goes onto the capacitor. The capacitor will have a white band which indicates that that's its negative there, and we connect the negative up to that like so. So there is our circuit all ready to go, and here we have the oscilloscope. And we're going to use the oscilloscope to measure the voltage across the capacitor. An oscilloscope is basically a piece of electrical measurement equipment that's able to draw a voltage over time graph of a waveform at a particular point in a circuit. Time is measured horizontally and voltage is measured vertically. The units horizontally are seconds per division, and the units vertically are volts per division. There is an auto set button, which is something you can press if you're not sure about the type of waveform you're going to be reading. In this case though, we know something about the circuit. We know that we're using a capacitor and a resistor. We know their values, and we know from previous learning that whenever we have a capacitor and a resistor in series with each other, they form something known as a time constant. When we multiply 100 microfarads with 100,000 ohms, we get a time constant of 10 seconds. And from previous learning, we know that it takes the capacitor 5 time constants to fully charge. Therefore, on our oscilloscope, we're going to want to set our seconds per division to a reasonable level so that we can get a good reading. And we do that using the seconds per division dial here. And by adjusting that on this oscilloscope, you will see how many seconds per division have elapsed. I can take it right down to a few microseconds if I want to, but that would be far too fast. So here I've adjusted it to 10 seconds per division, and you can see how slowly the trace moves across the screen. It's taking 10 seconds to travel every division. In the same way, the volts per division can be adjusted for both channels, but we're using channel 1, the red channel. It's adjusted here using this dial and red there. So it's adjusted using this dial and red in the bottom here, and at the moment that's at 1 volt per division. We have a power supply of 5 volts, so when we do the measurement, we should see our trace go 1, 2, 3, 4, 5 divisions up. We need to connect the scope. We have 2 ports here, channel 1, channel 2. It's simply push and twist. The probe itself has a ground clip, and that will connect to the ground of your circuit. There. Just like that. And the probe itself connects to the other side of the capacitor like that. And that is all you need to do to set up the connections for this circuit. Just make that a little, so you can see that a little better. Now that the circuit's set up, we are interested in the reading on the oscilloscope. I'm just going to speed this up so that the trace comes through the other side. There we are. So all that you need to do at this point is just switch on the power supply and then watch the waveform as the voltage across the capacitor. So we press the power supply on, and we can see the waveform beginning to appear here as the voltage across the capacitor charges. And because it takes 5 time constants to fully charge, it should be fully charged when we have completed 5 divisions on the oscilloscope. So at this point we've done 3, 3.5, coming up to 4. And what we're going to do, we're going to press the run stop button when we reach 5, that's this point here. And we stop it like that. And this button will freeze the display. And that is the amount of time it takes the capacitor to fully charge. It doesn't quite reach 5 volts. If we count the vertical divisions, 1, 2, 3, 4, about 4.5. And the reason it now doesn't quite reach 5 volts, 2 reasons. One is that the oscilloscope, although it has a high resistance, a high input impedance, will still draw current from the circuit. And therefore, if it's still drawing current from the circuit, we will get a volt drop across this resistor here. And therefore, all of the voltage can never be dropped directly across the capacitor. So what we have here is a good approximation, but we don't have the whole story because of the input impedance of the oscilloscope. We're now briefly going to look at the cursor utility. That's this button, and if we press that on, we will have 2 menus come up here, and pressing the H1 button will switch on the cursor types, and we can choose 2 different types, either voltage or time. If we select voltage, we get horizontal cursors here. These are the cursor controls. So for example, I could measure the amplitude of our voltage by setting one cursor at the bottom of the waveform here, and the other at the top, and then we will take the reading there. That gives the cursor reading, and this is the change in Y, the change in the Y dimension, which gives a reading of 4.56 volts. As we said, it can never quite reach the 5 volt criteria. We could measure the voltage after one time constant. In fact, you're going to be asked to calculate the voltage after one time constant. We've set up the scope so each horizontal division corresponds to one time constant. Therefore, by tuning the top cursor so that it intersects with the waveform as it passes one time constant, we can find the voltage at that point. And this tells us the voltage is 3.04 volts. If you were to work out this as a percentage of the maximum voltage, 5 volts, or in this case 4.5 volts, you will see that after one time constant, the voltage is approximately 63% of the maximum. Calculation will confirm that when we come to the calculation part. By choosing H1 again, we can select time, and this time we get vertical cursors. And it's the same procedure. If we were to measure one time constant, it should confirm, as we've got the scope set up, that it's about 10 seconds. Just move that cursor along a little bit further. And there and there. Once again, we take the reading from here, is the change in the X dimension, and that's shown to be 10 seconds. The cursors and some of the other functions for this oscilloscope are much more powerful and flexible when you use them with a computer. In fact, this oscilloscope is much better when it's hooked up to a computer and used as a virtual instrument.